So we start from trilayer, so trilayer of niobium, aluminum oxide, niobium, and then of course by select anodization and further isolation of the top electrode of the junction, of course, we make an etching of the surface of the niobium, of the top niobium, small niobium here. So, and then we deposit the ferromagnetic layer, in the case of permalloy, which is the red layer here, and at the end, of course, the wiring, which is the second electrode, the superconducting electrode of the system. So the configuration is the one that I showed before. So S from the bottom to the top, S I insulator, S small, so small thickness, ferromagnetic, and S again. So in this case, of course, the IV curves can be measured, the pattern can be measured, and so on. We test for this configuration two thickness of niobium, one of 10 nanometers, so close to the coherence length that we expect for the niobium, polycrystalline niobium of our fabrication systems, and another one of the order of 30 nanometers. So, I mean, we expect something related to something like three times the coherence length of our niobium, and we use in both cases 3 nanometers of ferroalloy. So we are, in the case of palladium iron, we are in the limit of that material, and also in this case we have to use remember Tesla in order to have the splitting. And here again, in fact, in this case, of course, the fields are much lower. If you look to the problems from a theoretical point of view, now there is in this reference here you can find the arguments that I'm trying to express now here. So in the first junction, that one with the niobium 10 nanometers, we are more or less in according to this plot, we are more or less in this point of the red point that you see here, which corresponds to here to the thickness of the small superconducting layer, which is of the order of lower than the coherence length of the niobium, or in our case in 10 nanometers.